Good day and welcome back. This is part two of our discussion on arc length, curvature, and more. In this segment, we will focus in on the topic of curvature. And to get started, let me just give you a quick recall. In our previous section, we noted that for a space curve C, much like the one we have pictured, the unit tangent vector is defined to be the derivative r prime divided by its magnitude. And the observation I want to make is that if we go to any point on this curve, we can draw an associated unit tangent vector. So this unit tangent vector that we draw at each point, it will be tangent to the curve, i.e. going in the direction that the curve travels, and it will have exactly unit length. And as we draw this at more and more spots, we see that as the curve is changing directions, so is the unit tangent vector. So the big observation that I want to make, which might seem obvious from the picture, is that the unit tangent vector changes direction as t varies. And what we want to do in a sense is kind of measure, how much this changes direction. And the topic of curvature is all about measuring, so it measures how much the curve changes direction. So for example, something like maybe say a line, that doesn't change direction, so it shouldn't have a curvature. The curvature should be 0. Similarly, if you are just going around in a nice concrete circular motion, the curvature should be maybe constant in a sense. So on our next page, we'll give some definitions of how we calculate the curvature, and then we'll move on to investigate a few examples. So the curvature of C at a point measures how quickly the curve changes direction. And remember, when we're thinking of this curve C, we're thinking of a vector valued function, r of t. And we will present two formulas for the curvature, and depending upon the context or scenario, you would choose whatever is most appropriate or efficient. So the first definition of curvature is that it is the magnitude of t prime divided by the magnitude of r prime. And compared to our previous observation that the unit tangent vector is changing directions, it's reasonable maybe to see this t prime appearing. And also let me really emphasize the fact that curvature, represented by this quantity kappa, is a constant, i.e. a scalar value. It's perfectly fine for the curvature to depend upon t, but it's going to be a scalar type of value. It's not a vector, it's a scalar. The other definition for curvature is that it is the magnitude of r prime crossed with r double prime divided by the magnitude of r prime cubed. And as mentioned, depending upon the scenario, we would pick whichever one of these formulas is more appropriate. And these two examples will kind of illustrate that idea. So in the first example, let's find the curvature of this helix that we worked with on the previous page. So in order to find the curvature, we need to do some type of computations. At a minimum, we need to get started with, what is r prime and the magnitude of r prime. And that's going to guide the rest of the work. So r prime, we differentiate component by component. So 2 cosine 5 minus 2 sine t. And as we noted on the previous example, the magnitude of r prime in this case is the square root of 29. And since we've already done the computation, I'm just going to write down the number. And whenever we see this scenario where the magnitude of r prime is a constant, I will typically proceed with the first version of the formula. But that's not to say you couldn't use the second version as well. And the real reason is we just simply need, kind of two more computations at this point. The unit tangent vector is going to be r prime divided by its magnitude. And dividing r prime by its magnitude is simply multiplying by a constant, 1 over the magnitude of r prime. So that's times 2 cosine 5 minus 2 sine. And t prime, we would differentiate each component individually. And when you do this, it's perfectly fine to leave the constant out front or to push the constant into each component. I prefer to just leave the constant out front because it's one less thing I have to worry about. So differentiating term by term, minus 2 sine, 0, minus 2 cosine. So it's a very methodical approach regardless of the formula we choose to use. Reminder that if you want to find the magnitude of a constant times a vector, you would take the absolute value of the constant times the length of the vector. So in our case, we would take the absolute value of the constant, which is already positive, so the absolute value is not required, multiplied by the length of that above vector. So 4 sine squared plus 0 squared plus 4 cosine squared. And note this quantity under the square root is 4, and the square root of 4 is 2. And we can now put this information together to have the curvature. So the curvature, using this first formula above, would be the magnitude of t prime divided by the magnitude of r prime. The magnitude of t prime is 2 over the square root of 29, and the magnitude of r prime is the square root of 29. And these combine together to be 2 divided by the square root of 29 times the square root of 29, which is 2 over 29. And two observations to make here. One, if you have any questions about that algebra, remember a over b divided by c is a over bc. And furthermore, since we're calculating the curvature of a helix, which wraps around, in this case, the y-axis at a nice, constant, uniform rate, we should expect that the curvature is a constant. So let's go ahead and now finish this curvature discussion with one more example. Find the curvature of the defined space curve, and note the hint, one of the curvature formulas works more efficiently than the other. What I would like you to do is to pause the video, give yourself 5 or 6 minutes, and see if you can come up with a curvature formula. Okay, so now assuming that you've done that, let's get started. We need a few kind of key ingredients. We have r in its vector form would be 0 t cubed t squared. R prime is given by 0 3t squared 2t, and the magnitude of r prime would be the sum of those components squared. So 9t to the fourth plus 4t squared. And this is an important quantity. It's really kind of guiding me towards which formula I'm going to use. So note the unit tangent vector in this case would be 0 3t squared 2t divided by its magnitude. And because this magnitude of r prime depends upon t, you would really have to push this into each component, and you're going to be using, say, a quotient with a chain rule, and the derivative's not really going to be all that efficient to calculate. So because of this quantities of t's appearing in r prime's magnitude, I'm going to use the second formula that we have identified. So the other key ingredient I would need is r double prime. So r double prime would be given by 0, 6t, and 2. Now I'm going to create a little more space, but hopefully we all see that formula at the top of our page. We have all of the key ingredients. Now we just need to combine them appropriately. So we need r prime crossed with r double prime, which remember is a 3 by 3 determinant, ijk across the top row, the vector coming from r prime in the middle row, and r double prime in the bottom row. And if you were to calculate this out, and I realize it's just a step or so, and I'll leave that to you, you would end up with minus 6t squared, 0, and 0. So the magnitude of r prime crossed with r double prime works out very nicely here, almost too good to be true in a sense. You would get the square root of 36t to the fourth, which is 6t squared. And we now have all of the information that we need for the curvature. So a reminder of the formula we're using, r prime cross r double prime's magnitude, so a number, divided by the magnitude of r prime cubed, another number or scalar value. In this case, it would be the 6t squared divided by 9t to the fourth plus 4t squared. And note, when it's raised to the 1/2 power, that's the square root, which we see. But we want to cube it, so we multiply that 1/2 by 3. So if you cube a square root, it becomes a 3/2 power. And in terms of simplifying, I think this is about the best that we can hope to do. Now that completes our discussion of curvature. In the next few videos of this series, we will move on to talk about the more portion of the title. Things like unit tangents, unit normals, binormals. So there's quite a bit more to come. So stay tuned and take care.